start over again and quickly go through a couple of things. Is that all right?
Yes, please.
Yeah. All right. So earlier I was saying that I will start with the Nobel Prize in physics or in astronomy, and I'll try to relate my works with their works because the Nobel Prize was about the black holes, and I'm also working on the supermassive black holes using different telescopes. So the Nobel Prize was given, can be divided into two parts. The first one is theoretical part, and the other half is the observational part. For theoretical part, Sir Roger Penrose received uh, the Nobel Prize for proving that actually, if you follow general relativity, that actually the black holes are possible configurations. That's what he proved with his work. And Reynard Genzel and Andrea Kias later actually observationally proved that there is actually supermassive black hole at the center of our own galaxy. So, as I briefly discussed earlier, it all starts with general relativity. General relativity by Einstein is slightly different, takes different approach than the Newtonian gravity or Newtonian theory of gravity. We say that every two objects in the universe attract each other, so there's a gravitational force between two objects. But in Einstein's general relativity, things are a little different. What happens is the any thing with a mass curves the nearby space-time, and in that curvature, the nearby objects follow. So that's a different approach to look at the gravity that's in his general relativity. Uh, uh, but it was interesting to note that Einstein himself didn't believe in black holes, which would be the immediate consequences of theory. Uh, so the first one who pointed out this possibility was Schwarzschild, Karl Schwarzschild, an Austrian physicist, who actually solved his equations and showed that actually there are black holes and event horizon and black holes and singularity kind of thing. But the robust proof of the fact that black holes are actually possible once you accept general relativity, once you follow general relativity, then uh, the black holes are are possible. That's what he proved in his works in 60s and in 70s with Stephen Hawking or other his colleagues. Um, so I had opportunity to meet him also. So I'm showing you my picture here with him. The other half was for okay. So in theory, black holes are possible. The question would be, can we see them? That would be the immediate question to ask, and where would we find them? And by then there was a lot of activity in astronomy and physics that everyone was convinced that every galaxy actually had a supermassive black hole at its center. And then the question would be, where would we look for such black holes? And for us, like Sun is our star, closest star. Uh, Milky Way is our galaxy, so we'll have to look for a black hole at the center of our galaxy. But as you can see in this picture, the center of our black hole, our center of uh, the galaxy is so much obscured by the dust and clouds that we can't see it in optical band or in optical emission. It's not just possible. So that's when they thought of this the Andrea Ghia's groups. What they did was that they tried to look through not the optical telescope but the infra-red telescopes, and which can actually penetrate through the dust and cloud that's in between the center of our galaxy and us. What they did was they pointed out or they spotted a couple of stars near the center of a galaxy, which is known as Sagittarius A. And then a couple of stars, as you can see in this picture, from 1 SO1, SO2, SO5. So they track the evolution of the trajectory of these stars, and from there that they see that there was something going on there. Let me quickly show you a video of it's a let me. So so this is a video. This is a time lapse. You can actually see the data here, and that's all the stars. So you see that we follow the trajectory of the stars over many years. And if you combine this with Kepler's laws or Newton's laws, then you find out that this is something very massive at the center of, which is shown by here star. So that's the region. So then you quickly come with the conclusion that there's something massive at this point, and and when they calculated, that turned out to be 1,000,000 times our solar mass. That's a black hole that has a mass 1,000,000 times greater than the sun of the mass. So with this, they actually received the Nobel Prize. And so continuing on with black holes a little bit. So black hole roughly can be divided into two categories. One is stellar black hole, and the other is supermassive black holes. The stellar black holes of the size of the sun, or a couple of times, 7 to 8 times. Supermassives are million to billion times. And the question you can ask is, how do they form actually? So here I a little bit discuss about the formation of the black holes, which is related with the life cycle of the stars. Everything starts with a clump of gas, clouds, which is called nebula, right here. I'm sorry. And now this over the time, the cloud contracts and clumps together because of the gravitational force, and then it can take one of these two top or bottom tracks depending upon how massive the clump is. So if there's not much mass in here, so it goes up here and becomes slowly the clump contracts, and because they come closer to the center, everything starts spinning and forms a disk called accretion disk. And over time, a protostar takes shape, and slowly over the time that becomes a star, and the star, meaning the hydrogen at the center, fuse to helium, and that which provides the outward pressure, while the gravitation force keeps on pressing inward. So it balances us for some time, and that's how it becomes a stable star for a long time, actually some million to billion years. And after some time, the hydrogen it runs out of hydrogen fuel and starts fusing heliums, but only up to some iron, and then after some time it blows off and becomes very big, and that's this phase is called red giant. And someday the sun will also be a red giant, and the sun will become so big that it will engulf Mercury, Venus, and even Earth. It will be engulfed by someday. And if for a not so massive star, then after the red giant, the outer layer will be blown off. So the central part contracts and the outer part is blown off, and that stage is called planetary nebula. And what remains inside is something called white dwarf, and that shines for a while, and it slowly loses heat and energy through radiation, and then someday it ends up being a brown star, a small, not a cold, kind of what they call brown dwarf. This will be the fate of a star that's not so massive. Well, if it's really massive, let's go down follow. So again, start again the nebula, and it becomes a protostar, and then becomes a larger star, starts hydrogen fusion of hydrogens to make heliums, and then once it runs out of hydrogen, then it starts fusing helium, and then again gradually heavier elements are formed. But at some point again, you will run out of fuel. The outer shell will expand and become very supergiant, and after some time, it will also go through a stage called supernova, in which the outer part will be blasted off into space with tremendous energy, and the inner part will just be crushed to a small points. And if the remaining, so why large mass? I've been telling you is that now the remaining core is still massive like 3 or 4 or 5 solar mass. So in this case, then it might become a neutron star. What is a neutron star? A neutron star is a star made up of neutrons. What happens is all the electrons, even the gravitational force becomes so strong, so overcoming, that all the electrons are pushed or crushed into the protons to make neutrons. So all you have is neutrons only. And then you can see the neutron stars in the form of the pulsars, which you might have heard about them, the pulsars. And if the star is even massive, then the neutron star, there's something called degeneracy pressure by neutrons, which is overcome by the gravity, and it even crushed further and becomes a black hole. So that's how the stellar black holes form in the universe. So it's related with the life cycle of the stars. The other kind of black holes are supermassive black holes. And how do they form? And they probably form. This is not quite as obvious as in the case of the stellar black holes, but they grow as the galaxies in clusters slowly merge over a period of time. You might have heard that someday our galaxy Milky Way and our nearest galaxy Andromeda will collide someday after millions and millions of years. So they're in the process of colliding each other. So that's in a cluster. That's the fate of the galaxy. After some time they merge, and when they merge, they grow, and then the black hole grows and grows, and that's how they form the supermassive black hole at the centers. So that's how and of course you have seen the picture from the last year, the shadow of the black hole. This is the black hole at the center of the galaxy M87, which was taken by EHT, Event Horizon Telescopes. So that means we actually can see the black hole. Actually, this is not quite true. We cannot see the black hole. That's why it's a shadow of black hole. But it attracts, so it attracts anything around it, and then forms a accretion disk, and that becomes so hot that it starts glowing, and it becomes very, very bright. So it may sound surprising, but the biggest black holes, which are assumed not to be seen, are actually the brightest. So biggest black hole are the brightest ones. Okay, then I'm going to talk about this active galactic nuclei, which is where these black holes sit. This is so galaxies. Again, galaxy can be roughly divided into two parts: active and non-active or dormant. The active galactic nuclei are the galaxies which is fed by the accretion disk It's glowing. It's eating a lot of matter. So they were glowing. In some cases, it's jets, and it's producing a lot of energy and heat, light, everything. So this kind of galaxies are called active galactic nuclei. Actually, the central part, only the 10% of the central region is called active galactic nuclei, and they are very very active. So in that sense, and they are very luminous. Actually, they can be 100 to thousands time high luminous in comparison to the normal galaxies, and they can be seen in any frequency, multi-frequency. And the interesting thing about them, which is very important, is that the flux changes rapidly in all frequencies, and you can also see the broad emission lines, and that's important. The emission lines tells what matter is there. It's made up of. From periodic table, we see that corresponding to the energy lines, to energy levels in a particular atom or molecule. And you should be able to see some of the lines, the spectra. That's how we analyze the stars and the galaxies. So broad emission line is that something is going very fast around something, and that means the line becomes broadened. So these are active galactic nuclei. So in this cartoon, you can see that the central part is the massive supermassive black hole, and that's surrounded by something called accretion disk, which is matter accreting around the black holes, and from there, from here, you see that two bipolar jets are coming, which are relativistic jets. Actually, the plasma matter shoots off in these directions with relativistic speeds, and this is very interesting source of high energy emissions. And these are the hot topic of the research in these days: the formation of the jets, the launch of the jets in the heart of this AGN. So these are AGN, and they have billions supermassive black holes that are as big as billion times the sun, the mass of the sun, and they are very compact, meaning that the billion solar masses black hole is compact, resides within the space of the solar system. So very compact, very compact. And as I told you earlier, the bipolar jets, you can see the bipolar jets. In this case, I'm showing you three sources. One is this Cygnus A, and then these are the jets. And these jets start from here. This is the center of the black hole somewhere, and they are launched from there, and they travel up to parsecs to megaparsec distance, which is a huge distance. One parsec is about 3.26 light years, which is how much time it takes for light to travel. So one parsec is 3.26 light years. So it takes light, but that means it takes 3.26 years for light to travel that distance, and the light travels about 300,000 kilometer per second in 1 second. So it's even for the light that travels fast, it takes thousands of years to get to that distance. So you can see these jets. They actually can see these were taken from telescopes, and the lower one is the M87 jet. The same M87 we saw the black hole image, and you can see actually it's seen in optical. So you can see a ray of something coming out of a very luminous source. That's actually is the relativistic jets that's coming out of the black hole, just due to the activity of black holes. And here's another case the Asian called 3C31, and in this case you can see the jet is kind of twisted. That will probably mean that it's going. There's a lot of intergalactic material, and it's moving through a dense part of the intergalactic material. That's why it probably looks jagged. This kind of. So these are Asian jets, and the topic I'm going to come is blazars. So the blazar, what are blazars? So as I told, Asian has a supermassive black hole at the center, billion times solar mass, and it's surrounded by a accretion disk, kiloparsec, parsec scale accretion disk, and from there the jet is ejected, relativistic jet is. So if the jet is directed towards Earth, as you can see in this picture, or if it's within 10 degrees, that jet is aligned to the Earth, then this kind of sources are called blazars. And there's a reason why these are special, because the plasma coming out comes out in relativistic speeds, like very close to the speed of light. And when some light travels, or some sources travel with that speed, then the effects are very dramatic. Something called headlight effect. It becomes the light then is preferentially directed to the direction of motion. So it's something like headlight. It's a focused light, so towards us. And so because of that, they become really powerful sources, ultra luminous, very bright, and very. They also become variable sources. And this class of sources are very interesting, and these are the dominant sources of the high energy emissions, like X-rays and gamma ray. I might talk about this later, a little bit later. So blazar are the Asians with jets, and the jets are aligned nearly to the line of sight towards Earth. Now, so I have to a little bit tell you about the electromagnetic spectrum. I think you might be familiar, but this is the only way we analyze these sources. The light is actually the messenger. It tells about what kind of matter there is, in what speed, which speed it is moving, what is the surrounding. So all we have is the light which we receive in our telescope, different kind of telescopes. Now, as you can see that the electromagnetic it's a wave, and that can be characterized with frequency or the wavelength. And as the wavelength increases, it goes through radio towards, becomes weaker and weaker, and becomes radio. And if the wavelength decreases, or alternatively the frequency increases, then it becomes more and more energetic, and it becomes very powerful. So in this picture you can see that. So that's how you have a very wide electromagnetic spectrum. And on the visible light, the light we talk about, usually whatever we see with our eyes or optical telescope, it's a very narrow band that you can see in this. This is a tiny window. So there's a whole large window through which we can see, although it's not visible. So you can see that. So to the right, it's infrared and radio waves, and to the left is X-rays, ultraviolet, X-rays, and gamma rays. Infrared. So I was talking about these infrared telescopes that we use to track the motion of the stars at the center of our galaxy. So these are, and then there were radio telescopes, which is in the form of the radio dishes, and then, but the high energy emissions is blocked out by our environment. So not much of ultraviolet or X-rays and gamma rays reach the ground because of the environment, or the ionosphere. So therefore, for this kind of analysis, you have to set up the telescopes in space. So we have all the X-rays and gamma rays telescopes are in space. So these are by NASA. So anything you have to study with these kind of rays, you have to rely on these space telescopes. So in my studies, in my studies of Blazar, I use all kinds of these telescopes, right from radio or optical or X-rays and gamma rays, which I will talk about this later. So let me start with these optical telescopes. So most of my research is the telescope is in Keck, Arizona. That's where how I was observing the Blazars or the Asian from there, and so our telescope was this 0.09 meter telescope that I was using for studying a lot of Asian. This was my main work during my PhD in Florida International University. And the other telescope I use is NASA Fermi telescopes. It's a gamma ray telescope within the band of 100 MeV to 300 GeV. So it's the telescope goes around the Earth every 90 minutes, about 90 minutes. So it is a wonderful instrument that studies the universe in gamma ray, and so you get capture some of the violent episodes that's taking place in the universe. Similarly, the recent one is telescope is the NASA NuSTAR hard X-ray telescopes that detects the sources which are emitting a hard X-ray. The hard X-ray is coming from them. So these are the kind of telescopes I use, and besides I also use the radio telescopes, which are mainly large dishes set up in USA or all over the world, from where we get the data and then analyze the sources. So now I come to my work. What kinds of work I was doing, I was involved in. So this is one of the work that I did in 2014. So this is one of the Blazars called S5 0716 Blazar, very famous, very highly variable Blazar. And what I did in this with this Blazar is that I made a campaign. I organized a campaign in which 30-40 observers all around the world, like 13, 14 countries, we kind of gathered and decided that we will track this single source for a long time, because you know that optical observations is only taken at night. Yes, you can't do that during day because there's sun. But if you want to track something like continuously, it's not possible to track a single source from a single position, because the length of the night is like after 6-7 hours. That's the typical length of nights, and you can't track it anymore. So what we decided is that let's spread all over so there are astronomers all over the world. So from India, from China, from USA, from Japan. So we will all track the same sources. So that's how I conducted this campaign, single source. And what you see is here something called light curve. So in x-axis you can see the hours in time. So you can see about 100 hours. And y-axis, as you see, is a flux, the measurement of this the energy it outputs in optical band. So as you can see, there's a lot of fluctuation. What that means is the light is coming from very compact region, somewhere nearby the center of the black hole, near the black hole, because it's all fluctuations coming very fast. And so this is one of the ways to explore the innermost region of the black holes. And we published this paper back in 2016. So you can see the astronomers all over the world, and I was leading this project. We published that back in 2016. And the other work I was working was I was studying a sample of these blazars using the NuSTAR telescope that I showed you earlier, the NASA space telescopes. And in this study, we studied the spectra and the light curves of many blazars. So in the top picture, what you can see is that it's couple of time is in kilosecond, meaning a couple of hours, and then the y-axis is again counts per second. This is the X-ray number of X-ray photons per second, and this is the light curve. So within a couple of hours, you see that the source changes. That's when we're looking somewhere in the accretion disk or the jet, where the emission is coming from. So these are powerful explorations of the jets and the accretion disk. And similarly, we're looking at the spectra, what's in the spectra of the source. So we see that some kind of power spectra there. And also we something called hardness ratio. It kind of loops around, that gives very interesting properties we can study about this kind of sources. And this was the work I was doing with my students here, and we published it back in 2018, and studying these kind of things. Then there's even more interesting part of these supermassive black holes is something called binary supermassive black holes. So in that case, what happens that two supermassive black holes go around each other. That is very fantastic. One of the most violent episodes in the universe. I can show you quickly show the picture of the NASA simulations, how it would look like. Not this one, I guess. So that's something there. So this is a simulation produced by the NASA. The two supermassive black holes, how it would look like if two supermassive black holes would go around each other. So these are the simulations. There's not real pictures actually. I'm trying to simulate what will happen, but we're trying to observe them through our telescopes. So one of the famous blazar that is believed to be the supermassive black hole, is binary supermassive black hole, is OZ287. So it is believed that you can see there's a black hole at the center, and there's a huge accretion disk. And there's another black hole which is kind of going into elliptic and in orbit that is in a making certain degree with the accretion disk. So every 12 years or so, it hits the secondary. So there are two black holes. First one, the bigger one is primary. The smaller one is the secondary. The secondary black holes, while going in its orbit, it hits the accretion disk every 12 years, and that way produces a large flares. Whenever something hits, it becomes bright, and that can be seen. And the right, you can see the light curve. This is the time, and in astronomy, the time is typically measured in something called Julian dates, and the y-axis is the flux, meaning how much energy it outputs. So it happens that from data is almost 100 years. So you can see in the upper axis, you can see 1900, 1920, so up to 2000. And you can see that every 12 hours you see these spikes. That's how we think that this is actually a supermassive black hole going around each other. So, and I also studies this source using our optical telescopes. So in this case, what you did is with my collaborators around the world again, we tracked this source, that's Blazar, using our optical telescope from 2007 to 2016, and we saw that there are actually fluctuations. So meaning that something going on here, maybe binary supermassive black holes of the pulsations in the accretion disk, something periodic thing is happening, and which is directly caused by the supermassive black holes, which is a consequence of supermassive black holes. And then we published this paper back in 2016. Similarly, this is another blazar called Galactic 0219 minus 164. Actually, the naming of these sources are like something called the position. This is according to their positions, the right ascension and declination. So in that case, what it tells is the right ascension is 2 hour and 19 minutes, and the declination is 16 degrees. So that's how the nomenclature of the sources are. So you can clearly see the fluctuations. And what does that tell us? This tell the possibility of supermassive black holes going at the center, and this is a very exciting topic. And this is another source. You can see the fluctuations, which we saw through radio telescopes, and the period of this particular source turned out to be 560 days. So every 560 days, you can see it repeat kind of periodic cycle. So that was published back in 2018. So these were opticals, radios, and now we're using this NASA telescope, Fermi telescope. This is a gamma ray telescope. So I found other this kind of periodic motion, periodic cycle or fluctuations in another source. Something. It's one of the famous blazar called Blazar Mrk 501. So this news was picked up by many international journals and reported. So as you can see that the light curve in this case is about 10 years, decade long, starting 2009 till 2019. And you can see that these fluctuations, you can see this kind of fluctuations that tells about the central engine, the black holes, and then the activity there. And similarly, then with another my Nepali colleague, Neeraj et al. So we studied more about these sources using this Fermi telescope, and then we found similar cases in many cases of blazars, and besides we had very interesting properties of these blazars and black holes, and which is reported in our publications. I think that's our time, so I think I will stop here. So if any questions.